Use a trigonometric substitution to evaluate the integral of 1 over the square root of x squared plus 16 dx. Let's start by prepping this first. This is the integral of x squared plus 16 to the negative 1/2 power. Now notice that the expression in parentheses takes the form of a variable term squared plus a number squared. It's x squared plus 4 squared. And that means this is a good substitution using an arctangent. So we're going to force the substitution. Theta equals the arctangent of the variable x divided by the number 4. Now to force a substitution, we have to first solve it for x. So this means the tangent of theta is equal to x over 4, or if you'd like, 4 times the tangent of theta is x. Now that we've reversed the roles of x and y, let's differentiate, treating theta as the variable. So we'll have 4 times the secant of theta quantity squared is equal to dx d theta. Multiply through by a d theta, and we get 4 secant of theta quantity squared d theta is equal to dx. And this can always be fit. We replace the dx with this complicated expression here, 4 times the secant of theta quantity squared d theta, and then the x on the inside can be replaced with, there it is, 4 tangent theta. So we have 4 tangent of theta quantity squared plus 16, all quantity to the minus 1/2 power. Whew. Now let's see, this term in here needs to be cleaned up a bit. This is the whole point. This is going to be 4 times the tangent of theta quantity squared plus 16. Now what can we do with this? Well, this is 16 times the tangent of theta squared plus 16. Yank out the 16 and we have tangent of theta squared plus 1. But that's just secant of theta squared in the parentheses by the Pythagorean identity. So this means our original integral is actually just 16 times the secant of theta quantity squared, all to the negative 1/2 power, times 4 times the secant of theta quantity squared d theta. So let's clean this up now. Since this is a product raised to a power, we can take 16 to the negative 1/2 power times secant of theta squared to the minus 1/2, which is just a minus first power, times 4 secant of theta quantity squared. Now that it's a product, we can clean up here. Notice that this is nothing more than 1/4. So the 1/4 and the 4 cancel, and that leaves us just with the 1. And also secant to the minus 1 times secant squared is just secant. So this becomes the integral of just secant of theta alone. That's one hell of a substitution. When we integrate this, we get the natural logarithm of the secant of theta plus the tangent of theta. And now we're ready to back substitute. Let's do that work up here. So back substituting, we get the natural logarithm of the secant of theta, which was the arctangent of x over 4, plus the tangent of the arctangent of x over 4. Now to solve these things, look at this. You've got 2 trig of arctrig combinations. These can always be simplified by drawing a triangle, and the triangle we need is the one from this right here. If theta is equal to the arctangent of x over 4, then with this reference angle, the opposite side should be an x, the adjacent should be a 4, and the hypotenuse should be x squared plus 4 squared. And notice that that's exactly the expression we started off with. Anyway, this is a natural logarithm. Now the secant should be the hypotenuse over the adjacent. So I have x squared plus 16 over 4. Plus the tangent is going to be the opposite over the adjacent, so x over 4. I should point out that the tangent of the arctangent should have just canceled anyway, but we were thinking ahead here. Alrighty. Notice that we can put this on a common denominator now too. This is the natural logarithm of x squared plus 16 plus x all over 4. Add a constant, and we have our definite integral. Booyah.